What we've developed here is a new kind of material that's essentially a synthetic muscle.
Dr. Hod Lipson runs the Creative Machines Lab at Columbia University School of Engineering. The muscle itself is actually easy to make, and its creator, postdoctoral researcher Ismael Möri mixed up some of it for us in the lab. It's made of alcohol and silicone mixed in parts A and B, coming together to create a smart material. But how exactly does the muscle work? The mixture of the silicone and alcohol creates tiny bubbles inside the soft structure that are so small they can't be seen with the naked eye. Low voltage electricity does the rest.
The electric current passes through, it creates heat, so this is like a small resistor. And that resistive heat causes the tiny bubbles to basically evaporate.
Our direction in our research is actually to gain control of this material and actually to let the robot control this material. This is just a basic material that allows you a high strain and high stress all in one, very cheap. It's 3 cents per gram lab cost. Can be prepared by untrained people. Any training will take less than 30 minutes.
Space of possible behaviors when it comes to soft machines in general is much larger. The design space is much larger. The behavior is much more complex. The dynamics are more uncertain, as you just said. There's a lot of uncertainty, or there's a lot of chaos in the way things behave. The behavior is frequently not stationary. In other words, the actuators will not behave in the same way every time. They'll behave in a slightly different way every time. So again, the design space is much more complex. The effect of the environment on the robot is much more pronounced. And again, all of these things are both challenges and opportunities. I think that because we, as engineers, have had a hard time modeling and building soft robots, we haven't yet explored all the opportunities. It's very difficult to take advantage of all these opportunities when it's difficult for us to even model and understand how soft robots behave and everything that's going on there in there. Evolution, on the other hand, is very good at exploiting all these dynamics of soft systems, but evolution takes a long time. And I think, we've done quite a lot of work on evolving soft robots, and in large part, it's because designing soft robots is very, very difficult. Big gap missing in simulation of soft matter, and in particular, not just soft, but fast moving soft robotic systems, right? So it's not just a sponge that deforms. It's really deforms in a dynamic way, in a controllable way, and possibly moves fast. To a large extent, it's just a chicken and egg. So there hasn't been a large community of soft robotics researcher. There haven't been a lot of products that involved that required simulation of soft matter. And so therefore the tools are not very developed. But as the community grows, I can certainly see this. There's more and more demand for soft robotics simulation tools, and that demand will be satisfied inevitably by new design tools. So I think that's already happening to a large extent. It's happening mostly driven by academia, but at some point it's going to be picked up by commercial tools as well. And we'll see, and that will sort of catalyze the transition, their material properties over time in a controllable way. So the range of materials that you can embed when you're going into the soft robotic paradigm, again, is much larger than the traditional rigid robotics. And I think, again, it's one of these areas where we have not even scratched the surface. When it comes to the physical body, we're still behind, but already robotic parts that have been optimized automatically are probably better than robotic parts that are designed manually. But the architecture of the robot is still a domain of human performance. The animals don't do. We want to fly from here to there very quickly in thin air. We want to go to space. We want to go. We want to do a million things that animals don't do. So we can only copy animals so much, but at some point we need to be able to use ideas that are inspired from biology, but really apply them in new ways. And again, thinking outside that box is really something that you can do in simulation, and it's harder to do by just copying biology. But the other thing I want to emphasize is that our human imagination is limited. It's very, even though we want to be able to think outside the box and come up with new ideas, it's hard, it's difficult. We humans cannot, it's very hard for us to think about, to be creative in areas where we don't have a lot of intuition. So we can have intuition about how to move with legs on the ground, but we have very little intuition about space travel, or about moving in deep water, or about flying, or about doing, or about moving in nanoscale or microscale. So if you really want to do breakthroughs and do big things, you have to be a little bit out there, thinking big, a little bit delusional even about what's possible, and go for this grand thing. Yeah, has this very progressive and an unusual license to do moonshots. And it's scary to do these big ideas, but I think it's very important, because if academia does not do big things, who's going to do that? But if you're a graduate student, you are limited to what you can do, because you can only work on one or two things at a time, and then it's a little bit more of a challenge. But again, I think those that really make it in a big way in academia are those that take the big risks. This ability to be comfortable with uncomfortable research topics. All right. So this is with these uncomfortable journeys, because when you are doing things that are uncharted areas, I mean, the only way to make a breakthrough is to go somewhere where no one has been before. That's almost by definition. And when you go somewhere where nobody's been before, you're going to be uncomfortable. For many reasons. There's not going to be tools, and there's not going to be metrics. Your papers are not going to be evaluated systematically. You're going to get a lot of rejections. People are going to question you about the risk that you're taking. So you got to be comfortable with being uncomfortable. And I think that's the most important quality. And sometimes it involves being delusional or less realistic. The way I like to phrase it is, if you think about, if you imagine yourself, having an option to do something that's, high risk, high reward, and it has 90% chance of failing, would you do that? So, a reasonable person would say, no, I'm not going to do something that has 90% chance of failing. On the other hand, if you do 10 things that are each of them 90% chance of failing, then overall there's better chance than not that at least one of them will succeed. And so you have to get into that statistical frame of mind where you're doing lots of crazy things and one of them is going to work out. And that's called being comfortable with being uncomfortable. And most people want to make that decision in advance. What should I choose? I'm going to guarantee a success. And you can't do that. You have to do multiple things and take a chance. But if you do multiple things in parallel, then you increase your odds that one of these things will succeed, and you will have done the impossible, which is to to do something that's low odds. And later you can tell a story how clever you were